Now, independent on whether you want to start with size and share of wallet, or if you want directly start with recurring revenue, you need to find some way to calculate the customer lifetime. You need to find some way of finding out how long the customer will stick around. And this is what I want to focus in the next couple of slides. In order to calculate and approximate customer lifetime, the first thing we need to do is we need to understand that the relationships that companies and customers have fall into different groups, depending on two dimensions. The first dimension is whether the relationship is contractual or non-contractual. Some companies have the luxury that their customers sign a contract with them, which locks them in for a certain period of time. For example, whenever you make a gym membership, for example, you may sign a contract saying that you become a member of this gym for the next 3, 6, or 12 months, and you have to stay a member and pay your membership fees independent of how often you go into the gym. The same may apply if you make a mobile phone contract, for example, and the company gives you a free mobile phone. You expect to have a contract that lasts 1 or 2 years. Or if you do a magazine subscription, they may run 3, 6, or 12 months. You call these relationships contractual relationships. However, this is not the case for everyone. For example, you never signed a contractual relationship with your supermarket or with your credit card company that this will be the only supermarket or the only credit card company you use, for example. Now, the advantage of contractual versus non-contractual relationships is that contractual relationships are far more stable and predictable. If you are a gym and you want to find out how many customers you have, the only thing you need to do is you need to count all the contracts that you have. A gym can tell you that today they have 12,310 customers, and today they have 12,305 customers. And the difference between the 12,310 today and the 12,305 tomorrow is that over the next 24 hours, 5 contracts run out. A company like Amazon can never tell you how many customers they have. A company like Uber cannot really tell you how many customers they will have tomorrow. Nobody ever signed a contract with them. Probably none of the customers comes back tomorrow. The second dimension is continuous versus discrete transaction streams. Companies with continuous transaction streams mean that customers can decide when to make a transaction whenever they want. You can use your credit card whenever you want. It is not that your American Express card only works Tuesdays and Wednesdays between 8 and 4 p.m. This is different, for example, if you want to go to a live concert. If you want to go to a live concert, to a live theater or opera performance, it is the company that imposes a time on you. You can only go to a live concert at the time where the live concert actually takes place. So there is a discrete transaction stream because transactions can only take place at very specific point in time. If you combine this, you get to 4 different cases. The easiest case is a contractual relationship with discrete transaction streams, and the most complicated case are non-contractual relationships with continuous transaction streams, and we talk about both of them now. Let's focus on the easy case first. Assume we are a magazine, which means we have a contractual relationship, and assume that our customers all do magazine subscriptions for 12 months, and they can renew those subscriptions only at the day where the subscription runs out. We have 1,000 customers who started a magazine subscription on January 1st, 2000. On December 31st, 2000, the prescription runs out. We go to all of them and say, do you want to renew for another year? Yes or no? If they say yes, we have them for another year. And if they say no, we tell them you can never renew again in future. I know this is a stylized example, but stick with me because I want to use it to explain a very important concept to you. Assume that out of the 1,000 customers who made the subscription in year 2000, 800 renew a year later. That's 80%, 80 out of 1,000. Out of those, 650 renew a year later. 650 out of 800, that's also about 80%, 81% to be precise. A year later, 500 out of those 650 renew. That's again, roughly 80%, it's about 77%. So you see that on average, every year, 80% of the customers renew their contract compared to the customers we had at the beginning of the year. And you call this the retention rate. The retention rate is the number of customers who bought this year and last year in T and T minus 1 divided by the customers we had last year. Well, if we have a retention rate of 80%, we know that we have a defection rate of 20%. It's just the opposite. 1 minus the retention rate is the defection rate. And if we know that we lose 20% every year, if you have a bucket that loses 20% of its volume every year, you know that after 1 divided by 20% or 5 years, the bucket is empty. You may have seen very often before the concept of retention rate, of defection rates. Sometimes people also call the defection rate a churn rate. And I'm using this example to show you that retention rates are so important because with a retention rate, you can immediately calculate the lifetime that a customer has. Of course, this is just an average. Does every customer stay 5 years? Obviously not. There are 200 customers who left after 1 year. And probably some customers will stay for 20 or 30 years. But if you know nothing about the customer and you know the company has a retention rate of 80%, you can say that on average, the lifetime is 5 years. Now, the problem is that this calculation of retention rate only works when you have a contractual discrete setting. So what about the non-contractual continuous transaction stream? Well, look at the bottom of this slide and look at customers A and B. Assume we are Amazon. Amazon has 10 million customers. And out of the entire customer base of Amazon, we pick 2 customers very carefully so that they fulfill a certain number of criteria. We call them customer A and B. A and B both purchased their first book at Amazon at the same day. We call it T0. They also purchased their last book at Amazon at the same day, which we call TX. Today, we are at capital T, which means there's a certain period of time, namely the one that elapsed between TX and T, that we have not seen these customers making any purchase. The key difference between A and B, however, is that between T0 and TX, A made 3 purchases and B made more than 3 purchases. If you look at these 2 customers, I'd like you to think for a second and answer the question, which one of these customers do you think will come back at some point in future? And which ones of these customers do you think is dead? One way to answer this question is to look at the inter-purchase time, the time that on average elapses between 2 purchases. If you look at the graph, you will see that customer A has a very long inter-purchase time. A probably only buys books every 6 months, while B has a much shorter inter-purchase time. B buys books every 2 or 3 months. If the time that has elapsed since we have last seen the customer, the time between capital T and TX, is large relative to the inter-purchase time, the customer has missed a lot of transactions. Customer B should have purchased at least once, maybe twice, since we have last seen that customer, but the customer didn't. While customer A should have probably only purchased once. And since customer B missed 2 transactions, while customer A barely missed 1, it is more likely that B will never come back than that A will never come back. What this graph tells you is that in a non-contractual setting where we don't have a contract, it can be very difficult to say whether a customer is active or not. The only thing that we can express is a probability, the probability that the customer is still alive. And this probability depends on the inter-purchase time, the number of transactions that the customer has done in a certain period, relative to the time since the last transaction. Now, there would be a couple of different ways to calculate this P alive, but let me give you one example. Assume we have a set of customers. On this slide, you have 10 customers, but it can be much more than 10. It can be 10,000, can be 100,000. For each of these customers, you know their past behavior, when they have purchased, and based on the past behavior, we want to predict their future behavior. We want to find out whether these customers come back in November and December, given what they did from January to October, and when they come back, how many transactions they will make. And there are 2 very fundamentally different approaches that you can take for this. Because every customer behavior has 2 components, a systematic component and a random component. Let's look at the systematic component first. You can say that customers usually have a very good reason for everything they do. You buy a bottle of champagne because you need a present for a key client. You buy a pack of biscuits because your mother comes over and she likes those biscuits. If we assume that customers have good reasons for what they do, we assume that the systematic part of their behavior is relatively large compared to the random part. And this means we can probably predict what people will do. You remember from the last session the concept of big data and artificial intelligence. Big data and artificial intelligence does exactly try to do that. Big data is all the kind of data that I can get about a customer, and artificial intelligence is one way how we can use that past data to predict what people will do in future. If you want a more traditional way of doing this, you can run a regression where, for example, you relate sales to income. You have learned these approaches in many statistics classes, and if you are not familiar with them, it might make sense to look up on YouTube the different types of approaches that you get familiar with them. Now, the problem with these approaches is that it assumes that people are largely systematic and not random. But very often this is not the case. If you look, assume you next time you go to a supermarket, and once you leave the supermarket, I ask you why you bought the items you bought. For many of them, you probably don't have an answer. Some items you simply bought out of habit, some items you bought because the packaging looked nice, some items you probably just put into your car without even thinking much about them. What this says is that in many cases, customer behavior may actually be random. And even if it's not truly random, it looks as if it were random. Now, if this is true, then that means that the random part of behavior is much larger than the systematic part, which means our regression-based or artificial intelligence big data-based approaches will not work. And this is the approach that we are taking now for the remainder of this session. For the remainder of this session, we assume that whatever people do is essentially random. So instead of collecting data about them and trying to use this data to predict what they will do, we just accept the fact that it's random and try to tell a story about random behavior. And the story we tell is as follows. Customers can either be alive or dead. When customers are alive, they purchase randomly but with a constant rate. Some people buy 1.5 times a year, some people buy 2 times a year, some people buy 0.5 times a year. Imagine that every customer has a little timer on their phone that tells them when they are supposed to buy new books, new toilet paper, new shampoo. They will buy it no matter whether they need it or not, whenever the timer gets off. Every day, a customer can die. Remember from the beginning, it can either mean the customer actually dies, it can mean the customer stops buying the product category or stops buying a specific brand. And different customers have different probabilities of dying. Here you have all these assumptions again on one slide. As long as they are active, customer purchase randomly, but they have a constant rate. Different customers have different rates. Every day, customers can die, and different customers have a different probability of dying. You can do a statistical model based on these 5 assumptions. Those of you who like statistics, they can look into the following slide. There's also an additional reading that explains this in more detail. Those of you who are not good in statistics, it doesn't really matter. What matters is that you can translate this story that seems very artificial into a series of equations. And then you can use those equations to estimate what people will do in the future to actually solve the question that we started with. And I want to finish with this last slide, which is a slide that compares how accurate these predictions are based on these models. And the bottom line is that these models can make incredibly accurate predictions. So if you want to predict the lifetime, if you're in a contractual setting with discrete transactions, it's relatively easy because you can use the retention rate. Based on a retention rate, you can calculate the churn rate, and based on the churn rate, the lifetime. But if you are in a setting of non-contractual continuous transaction streams, which is far more common, maybe instead of collecting a lot of data about your customers and hoping you can predict what people will do, accept that you cannot predict, and then try to use this randomness in a statistical model in order to predict what people will do. And you find more details on this in the supplementary reading that you find on the bottom of the slide and that you also find in the Dropbox folder.